In our second lecture in section 2.6, I want to talk about the existence and uniqueness of A inverse. So what does that mean? Well, our first question, when does A inverse exist, right? How do I know I'm going to be able to find A inverse? Because we saw in the last video, A inverse could exist, in which case we get one unique solution, or A inverse could not exist, in which case there's a couple of different situations that can go down, namely no solution or infinitely many. And this question is answered directly by the rank theory that we discussed in section 2.5, specifically video 2.5.6. So if you need to reference that, look at 2.5.6 lecture. Now, here it is in a nutshell, right? Remember that rank theory says if R, the rank of A, is equal to the rank of A augmented is equal to N, then there is one unique solution. Or if there are N variables and N pivots in A, not A augmented, but REF A, then there's one unique solution. And we saw in the last video, if there's one unique solution, then A inverse will exist. And so we can talk about the row echelon form, and we can talk about whether or not A inverse exists. And these two ideas coincide. In fact, these aren't even just one-directional implications. I should say that these are if and only if statements, meaning you can't have one without the other. And symbolically, we indicate that with a double-headed arrow. That is to say, one gives the other and vice versa. So if we are in the case where the rank of A equals the rank of A augmented equals N, then that will only happen if there is one unique solution, and that can only happen if A inverse exists. Now, if R does not equal R pound, if the rank of A does not equal the rank of A augmented, then there is no solution. And if there's no solution, then A inverse does not exist. But please note here that only one of these arrows is double-headed. Here, let me redraw these a little bit better. So it is true that if R and R pound are not equal, R is, if you want, R is less than R pound, then that is a double-headed arrow. That's a bidirectional statement. You can't have one without the other. But if there's no solution, that means A inverse exists, but that doesn't necessarily imply that if A inverse doesn't exist, then there's no solution. It could be that there's infinitely many solutions. And so this was case 1, case 2, case 3 in rank theory. If R does equal R pound, but they're less than N, we know that that is equivalent to the statement infinitely many solutions, and that would also imply A inverse does not exist. And so please note again that these two are not bidirectional. They're one-directional, meaning that if you in fact start with A inverse doesn't exist, you can't necessarily imply whether it's no solution or infinitely many solutions right off the bat. That requires some more work. But if you do know that A inverse exists, you get one unique solution and vice versa. That is bidirectional, and those are interlocked with one another. Now, the next thing I want to talk about is the uniqueness of A inverse. And what that means is the simple statement that if there is an A inverse, there's only one A inverse. And so there aren't multiple versions of this. So I guess I really should have started out this lecture with what is A inverse. So let's talk about that really quick. The definition for A n by n. Why does A have to be n by n? Well, if A is going to be n by n, or if we look at this first statement, if you have n variables and n pivots, then we have an n by n matrix. So for A n by n, and we always find inverses for square matrices only in this course. For A n by n, which is square, if there exists some Bn by n such that AB or BA in either order gives you the identity, then let me move this other statement here that we're going to work on. Come on, there we go. So if A n by n, for A n by n, if there exists some B n by n such that AB equals BA equals the identity matrix, that's n by n, then we say A is, let me organize this information a little bit better. Come on, program, let's go. Then 1, we say A is invertible or non-singular. You'll hear people say sometimes. Well, you probably won't hear people say that, but you might read it in a book. We say that A is invertible. What does that mean? It means that B is equal to A, and we write B equals A inverse. We write B equals A inverse. And there you have it. So that's our little definition. Let me make sure I'm not leaving anything else out. Let's see. Yep, we're good. Okay. So, how do I know that just because A times B equals I and B is the A inverse, how do I know that that's the only possible inverse? So that's what we're going to look at here, the uniqueness of A inverse. Suppose for an n by n matrix A, there exists both a B and a C, such that when I multiply A and B or A and C together in either order, I get the identity matrix. So what would happen in that case? Well, if that's the case, then AB is equal to I, but so is AC, right? And if that's the case, if they're both equal to I, then AB equals AC. Now, if AB is equal to AC, then I can multiply both sides of the equation by any matrix for which the multiplication is defined. And so don't forget that A is n by n, B is n by n, and C is n by n. So the matrix is defined in any order. Now, if I then take B and multiply both sides of the equation on the left by B, I could have chosen C. It didn't matter. I get the following. I can regroup this as BA times B is equal to BA times C. But I've already assumed that BA is equal to the identity matrix. So this is I times B is equal to I times C. But we know that the property of the identity matrix is, when defined, I times a given matrix is that matrix. And so this is equal to B, and this side is equal to C. And B is equal to C. So if there were two different matrices acting like the inverse of A, they would have to be the same matrix. So, for a given A where A inverse exists, A inverse is unique. So you never have to worry about finding multiple possible inverses. Okay, good talk.